Okay. So this is the general setting, and the LLM is going to be in the cloud. So it's constantly communicating. Okay. It is possible to have the LLM to lie or to be placed within the robot. Okay. But we are showing you the case where the robot is communicating with the LLM, or it's communicating with the program. Okay. So the camera node, we call it node, right, is sending images. And we are also prompting the language model. And based on the text and the situation, it's going to produce a plan. And that plan is sent to the robot, and the robot and the plan will be based on primitive actions that have already been defined. And it's the primitive actions, the list of primitive actions have been loaded to the LVM already. The TAs have has told me that they have done this. Okay. Oh, the lecture note has not been uploaded in the KLMS. Sorry about this. So let me upload this lecture note. Sorry about this. I will have this loaded and put, okay, wait a minute. So I've put the lecture note in the chatting box. And I'll have this lecture note uploaded in our KLMS as well. Can everyone have access to this? Please say yes if you have access to it.
It's already uploaded by TA in the KLMS.
Oh?
It's already uploaded by TA in the KLMS.
Oh, it is already. Okay. So why did someone said that has not been uploaded? So it is uploaded. Okay, so good. So it's very important that you understand this situation. To understand this situation. Okay? Second, in order to have access to this particular language model, and we have assumed that you're going to use language model from Google. Okay? And in order to do that, you need to have a key from Google. So you need to go to this site, sign in your Google account, click for an API card, key, not card, sorry. Check it, and you're going to use this in your program. You're going to load the key into your program, and this will allow the Google Cloud allow you to have access, because it needs to identify you. These are the three LLMs that you will have access to. There are pros and cons. Okay. So for instance, 2.5 Pro only allows you to have 50 requests per day, and the token size, okay, is going to be limited by this much per minute. Okay. 2.5 Flashlight is 1,000 requests, and the input token is this many input tokens per minute. Okay. And in your ROS, you should have this file, these files, and in the LLM planning file, there is, oh, not LLM, is it LLM file? Okay, this is a LLM planning file. This is an LLM planning file, and there's a software file, and inside the software file, you're going to have action groups file, and here are defined primitive actions. Okay, and the LLM will spit out a sequence of these actions to perform your task that was given to the LLM as a text prompt. Okay. This is sort of the skeleton of the Python program that you would have on your server. And your server will be connected to your robot. And there will be an internet connection. So essentially what you would do if the primitive actions are not defined, then you would be doing this. You tell the LLM, I don't know if you can see it, you'll tell the robot that it is a robot planner, and the possible actions are here, and what the goal would be. Okay? Move the red cube to the center and output the list of actions to achieve this goal. Okay? If the actions are not predefined, you would do this. And if we do this each time, then we eat up the tokens that we can use. Okay, so this action has been preloaded. That's what my TAs have told me. Okay. So here you go to the Google and you say what type of LLM you want. You're going to do ROS. Your Python is going to run on ROS. So you have to run this RCLPY for controlling the ROS2 nodes. Your actions, okay, your action is defined in that folder, software action group folder, and it's going to import all of that, okay? Then you're going to communicate you're going to initialize the Gemini client by your key. You put your key here, and you say you're the client. And then the LLM inference function. So you have an image. You have to tell it where it is, where the image is, okay? Because the camera node is going to give you the image, where the image is, and what the prompt is. Okay, you're going to give that. And these are some of the sequences. You have to tell it where to read it, load the image, convert the image to bytes to be sent to Gemini. So this program, the way it's written, the Python program acts as a middleware. So it's interacting between the robot and the LLM, which is in the cloud. Okay, so the information is sent to the program, and the program is communicating with the LLM. Okay, so the image is convert the image to bytes to be sent to the Gemini. Okay, and ask the model and get the response. You need to, you know, prompt it and get the response. Okay. And here's the main program, a little bit more detail. Okay, the prompt might be, there is a mobile robot equipped with a robot arm and a gripper. Some cubes are placed around the robot, and the goal is to move the red cube to the center. And you also load the image where the in this directory, in this path. And you get an action plan, and you make the response into the action plan. And you connect the Python code to the ROS2 system, declare action node. The action node is actually residing in the robot. Okay, so if you tell it to do, if you give it a sequence of predefined actions, okay, it will do the action. It will execute the action. Once you've done it, you're closing and shutting down the connection, and you're shutting down the RCLPY, okay? The details will be given to you and will be explained to you by your TAs when you're doing your demo, okay? But this picture is a very important picture to have in your mind, okay? So the robot might give you a set of instructions that look like this, okay? So that's how you would be interacting with the LLM. To be exact, the LLM is a VLLM, Vision Language Model. So the image is somehow encoded into tokens. The prompt will be segmented into tokens. The LLM will process the tokens and produce. And in your prompt, you would say you want the LLM to output a sequence of actions that it's predefined for achieving the goal, and it would spit out a sequence of actions. Okay, and that action will be relayed to the robot. And because it's predefined, it's just going to run each of the actions one by one. Okay? Just some information about this LLM or language vision model. The LLM was originally designed or initially designed for text. It takes text, and if it's in English, you can translate it in Chinese, you could translate it in Korean, and whatever. You can do some translation. It can have a dialogue. Okay, so whatever you ask, you might ask another question, or you can have a dialogue. Or if you ask for it, it might do some analysis for you. Okay. All this field is called natural language processing, NLP. Okay. So you understand, generate, and process natural language. That's what this field does. And an LLM is an area that is studied in NLP. But this NLP now is not only generally this NLP has a historical. It pertains to computer science, but now anyone who's doing research in LLM will have this knowledge. Okay, so let me just explain how you would do this. Get text and translations, or talk to you, have a dialogue with you, or do some analysis. So if you have a text, an input text, it is segmented, okay, partitioned, and it will, will be partitioned into some small words which are indexed. And 2437 is the index of that partitioned word, and that each index will belong to a particular vector here in two-dimensional vector. And the language model will look at this and produce an output vector. The language model, okay? So the language model will take the embeddings of the token, okay, and produce an output, and that output is projected back onto to the words, the index of the words, and you get the word, okay? To just say a little bit more about this tokenization and this index, here it is. We love NLP. It's split into smaller units, which we call tokens or subwords, or just subwords in this case. And each subwords will be associated with some index. Okay, so that is segmented or partitioned. Here, EOS stands for end of sentence, end of sentence. And that is mapped to a token, an index. And this index is associated with some vector. And this vector is what we call token embedding. Okay. And generally for large language model these days, there are about 10,000, 20,000 tokens. So 20,000 or 10,000, couple of thousand, 10,000s of these subwords are in the dictionary. Okay, and each one would be associated with some vector, embedding vector. Now, what is the large language model doing? It's looking at the tokens, so which are words, and it's producing a probability of the next word. So for instance, we love, okay, so let's say this is 3 tokens. It looks at we embedding vector and producing some output. Then it's looking at we love, and then it's producing something. Actually, not something, but it's giving you the possible probability of all the subwords or tokens. Okay, so what can come next? There are many, and the LLM will give you the probability of each one of them. Then the next word, if the next 2 input words, then it predicts the next one, and it gives you all the probability of the next possible ones. And of course, the one that you would choose will be the one with the highest probability. Okay, that is what we call a language model. No. So the language model is taking, you're predicting what the next word is. Okay, with the probability. Now, inside this language model is built on a thing called transformer, and the transformer does attention. Okay, what is attention? If you have a long input, it is able to correlate the prior inputs with various tokens or various subwords. So it's not here. Let's see. Let's say, for instance, you have okay. So the query. So the way it does this attention is you have a whole input. The whole input is a sequence of tokens that's coming in, and you are finding the correlation of the next one with all the other prior ones. Okay, and you do this correlation because you want to figure out the attention. In order to produce the output, where should you place your attention? Okay, so let me give you an example. I don't have the slide with me. The chicken crossed the road because the chicken did not cross the road because it was too tired. Now, the word it should correlate strongly with chicken and not with others, because it is referring to chicken. Now, if I had another sentence, the chicken did not cross the road because it was too wide. It correlates strongly with the road in that case. Okay? And the transformer is learned to do this. Okay? It's correlating with the past input. Okay? And it's doing this by having query, key, and value. So whatever is coming in is converted into query, key, and value. And the query is doing an inner dot product with the other key values of the prior words. But enough of that. And so that attention is automatically done by a thing called transformer. Okay, so it's just a function. It's just a function. And for your task, you don't really need to know transformer that well, okay? Because we are at a much higher level. We're not working with transformers, okay? So this is a transformer. It takes the input, it embeds it, it makes it into some vector. It tells the position of the input. So it's a sequence. So it's, let's say there are 10 words in a sentence. The positional encoding would say this is the first word, this is the second word, and so forth. And what it's doing cross correlation among the words. Okay. And the word that is in concern is embedded based on this cross correlation. Okay. So if you understood that, very good. If you did not understand that, that's still all right. Okay. So large language models have been built on basic unit called transformers. And transformers does attention. It's placing attention on the input, on certain parts of the input to produce the output. Okay. And the large language model also gives you the possible word probabilities. And the word that you would choose, or the word that it chooses, is the one with the highest probability. These are, some of the LLMs that have been published or reported. You start with GPT-1, GPT-2, GPT-3, and then we have GPT-5. And you can see that the size is increasing almost at an exponential rate, which means that it's becoming more exponentially more powerful. Okay. The size, the number of parameter size, I mean, it's 117 million, 1.5 billion, 175 billion. Okay, it's almost an exponential rise in the number of parameters. Number of parameters does not necessarily mean the capability of the LLM, but it's somehow related. But you can see that it's exponentially rising. The capability is rising exponentially. And it can do zero shot very well. What do I mean by zero shot? And this is very important. It doesn't need to learn everything in the training process. You can give some examples in the prompt. And based on a couple of examples, it can generalize. So for example, an LLM that has never learned Arabic, you can give some examples of translations of the Arabic, a couple, and after you've done that, in the prompt, in the input, it will be able to translate a lot of things in Arabic. Okay? So that's what we call a zero shot learning capability. Never seen it, never trained it before. You can also do, of course, few shot. You give it a few examples in the training set, and it's able to do it very well. And larger the model, the better it can generalize. And also there's this property about emergent abilities. Emergent abilities relate with zero-shot. It's like knowing or being taught one thing, one or two things, and knowing everything. Okay? That's what we call emergent abilities. And with larger models, you have more of that. Here is some pictures about, the various LLMs that have been presented or reported in the news. So this LLM, the first LLM, GPT-1 or BERT, came out in 2018. And since then, many LLMs have been reported. Some are private and some are public. Over the years, the number of parameters have increased. It's increasing at an exponential rate. Okay, so that's that's not a lot of information about LLM, but some information. I mean, you don't need to know how LLMs, you're not going to design an LLM for your robot. Okay, not in this X, but you may want to do that later on. Here is a robot called Can, and it's using LLM. So you prompt it, and you also give it the surroundings, and then you say, how would you put an apple on the table? This is the question. The LLM, without looking at the surrounding or having any visual knowledge, it's going to blurt out a whole bunch of possible actions. And then you also give it the picture of the surroundings, and based on the possible actions that it can take, it finds the value, okay, or the affordance. Some actions make sense with this image, some don't. So depending on how much it makes sense, a score will be given. Okay. So here is an example. I spill my Coke on the table. How would you throw it away and bring it? So, Coke is spilt. Possible actions with probability, and does that. And then it looks at the sponge, picks up the sponge. So the LLMs does the say, okay, it says what is possible, and there's a score, okay, just based on what it says, looks at the image, and also gives what it can do, okay, and based on this, you're able to have this, okay. There is a foundation model that is specific for robot. So we call this Vision Language Action Model, VLA, or the foundation model, Pi Zero. You can go Google search this and download this. And what this does, it takes the image, it also takes the prompt, the input, and this is fed into a pre-trained vision language model, and an action, a sequence of action will be given. Okay, so here it is. It's doing the laundry. Wash the dishes. Okay. I should also say, it's very important how you prompt your LLM. So for instance, here is one case. On average, Joe throws 25 punches per minute. A fight lasted 5 rounds of 3 minutes. How many punches did he throw? And the LLM outputs the value of 550. And you don't know how 550 was arrived. So you may want to do this. Ask the same question, and then let's think step by step. Okay, you have this A prompt, this is itself, and it would do it in a step-by-step manner and arrive at the correct solution. And this invokes chain of thought. Okay, so chain of thought. And maybe if you enforce chain of thought, you'll probably get a better, more accurate result or output. You know, this is just basic stuff. You know, it's 1.5 hours. My presentation was focused on your incorporating the LLM to the robot. Okay, I didn't say a lot about the working mechanism of the LLM, but if you're interested, you know, there are plenty of literature on the internet, or you may come to me and I take students and we train them to develop more fair, transparent, human-aligned LLMs. And you could do that maybe during the winter time. So that ends my presentation. If you have any questions, please ask. And of course, I'm expecting that all of you will be using LLM for your final project. Okay? Now, what I've shown you is a situation where the LLM is in the cloud. It's possible the robot that we have purchased has enough memory for you to download some freely available LLMs into the robot. And you can train it. Train it would require more memory, as much as the memory of in order to load up the LLM. So that's a possibility in your project. 네, 질문 없으면은 여기서 마치도록 하고 마지막 시간, so the third lecture will be about reinforcement learning. So based on your sensor input, what action needs to be taken to achieve maximum reward? And maximum reward will be related to the desired target state or the goal. Okay. Thank you for being with me, and this will end my lecture on LLM. Have fun.